Hello everyone, welcome back to another video from Exam Essentials. Today we are basically going to discuss Unit 1 of January 2025, and without further ado, let's get started. The first question says, what is the total number of atoms in 8.8 gram of carbon dioxide? Now, in order to solve this type of problem, the first things first, you have been provided with the molecular mass of carbon dioxide, and of course, the Avogadro constant is provided, which is about 6.02 times 10 to the power 23. So, in order to get that, we need to get the amount of moles for carbon dioxide. So, let's just find it out, which is equal to moles is equal to 8.8 divided by 44, which would lead us to a value of something like which is about 0.2, I believe. And then if you want to find the total number of atoms, we need to multiply the number of moles with the Avogadro constant, which basically states that per mole represents about 6.02 times 10 to the power 23 atoms. So if we do that, 0.2 times 6.02 times 10 to the power 23. Now, if we write carbon dioxide's molecular formula, you can clearly see that there are three types of molecule in per molecule of carbon dioxide. So that would basically sum up that there are three atoms per molecule. Okay, so we just need to multiply 3 with our whole calculation, and the resulting value would be about 3.612 times 10 to the power 23 atoms, which will obviously be B right here. Moving on to the next one, how many moles of ions are there in 40 cm cube of a solution of 0.050 mole per dm cube of magnesium nitrate? Now, in order to solve this type of problem, we need to get the basics of concentration and moles. First of all, let's find the moles of MgNO32 present in the solution. So the moles would be 40 divided by 1000 times 0.050. That would eventually give us around, I would say, 2 times 10 to the power minus 3. Now, of course, there are ions of Mg2 plus and we have NO3 2 minus, and of course in each solution we have two ions per solution, two ions or two nitrate ions per solution of magnesium nitrate. So in total we can say that in per solution or per mole we have three ions present. So we need to multiply 3 with our total amount of moles we got by dividing by basically using the concentration and the volume. So in total we would get 6 times 10 to the power minus 3 mole as our correct answer. So that would be C down here. Okay, the next question involves a water molecule containing the isotopes of hydrogen and oxygen. Hydrogen 1, oxygen 16 has a mass of 2.9908 10 to the power minus 23 gram, they say. Now, according to this question here, they say what is the mass of an atomic mass unit measured in grams? Okay, now in order to solve this type, we need to basically check out what is the data provided in the question. Well, we do have the atomic mass units of oxygen 16 and of course hydrogen 1, which is about 1.0080 AMU. So let us calculate the total mass of the water molecules in terms of atomic mass units. So in water, we do have water, which is H2O. So we have two molecules of hydrogen and one oxygen atom, right? So the mass of two hydrogen atoms would be 2 times 1.0080, which would basically give us 2.0160 AMU. And on the other hand, the mass of one oxygen atom would be about 15.99. AMU as stated down here. So the total mass would be, if you just add both of them up, that would provide us 18.011 AMU. That's right, if you just add both of them up. So now that you've got the total mass, what they say here that the mass of a water molecule in grams is provided is about 2.990 times 10 to the minus 23. So if you want to find the mass of an of an of one mu, what you need to do is just you basically divide the mass provided in grams right here, 2.9908 times 10 to the power minus 23, divided with the one that you just got down here, which is 18.011. So if you basically solve it, what we get is about 1.6605 negative 24, which would eventually lead us to option C right here. So that is how you basically solve problems associated in finding mass of in atomic mass units if gram and the required data values are provided. Moving on, the next question is about NX04, which is an oxide of nitrogen. As you can see, they give you the percentage by mass of oxygen in this oxide, which is about 69.57%. How do you find the relative molecular mass of this oxide? Now, the best way in order to solve this is that you just have, if you can find the value of X, you can easily find the relative molecular mass of this oxide. Now, in order to do this, there are many ways basically. The first things first, let us at first find the relative molecular mass of the individual constituent elements present in this oxide of nitrogen. So the MR of nitrogen down here would be about 14x, while the MR of oxygen here would be 16 times 4, that would be 64. So what will be the total mass? So the total mass is going to be about 14x plus 64. So that is the total mass of basically of this whole oxide down here, this gram per mole. Okay, now uh, now the next part is, since we're provided the mass of oxygen in the form of percentage, so we can use this formula down here, which is that percentage of oxygen is equal to, of course, mass of oxygen divided by total mass of oxide times 100. So if you basically plug in the required values in this equation, which would be 64 divided by 14x plus 64, which is equal to, if you convert 69.57 by multiplying with 100, that would be 0.6957. If you just place it down here, and then if you just solve it for x, you'd get about x is equal to 2. So if x is equal to 2, that would be N2O4. And if you simply find the relative molecular mass of this oxide down here, that would be 14 times 2 plus 16 times 4, giving you about 92 gram per mole. So our answer would be B down here. Moving on to the next part, 4 different solutions containing chloride ions, while 3 of the solutions contain the same number of moles of chloride ions. Okay, which solution contains a different number? So let us at first find the moles of each and every solution down here. For this one, if we just do it, 15 by 1000, I believe, times 0.80 would basically provide us about 0.012 mole. 0.012 mole. So the chloride ion per hydrochloric acid will have a 0.012 mole basically for this solution. Again, if you check out the moles present in the iron 3 chloride solution, that would be 10 divided by 1000 times 0.40, giving you about 0.004 mole. And if you check out iron 3 chloride, so the this is basically the formula which basically indicates that the chloride ion per FeCl3 will be 3. Okay, so 3 chloride ion is going to so in per molecule 3 chloride ions is going to have a mole of 0.04. Again, if you check out the next one down here, which is 10 divided by 1000 times 0.90, you will be getting about 0.009 mole. Okay, the next part, again you can see that the chloride no, this is about 0.012, slightly a mistake, I believe. Sorry, so it is about 0.009, sorry, it is about 0.009 mole. Now again, you can clearly see here that since magnesium chloride MgCl2, so that means per molecule consists of 2 chloride ions basically. So if we just multiply 2 here, we'll be getting 0.018 mole basically. Okay, so that is basically a different number that we got, whereas in this case if you check out, if you multiply 0.04 since with 3, since we can clearly see that per molecule consists of 3 chloride ions, so that would give us about 0.012 mole again. So the first one, A and B, are kind of identical as you can see, while the third one, C, is not identical because it is 0.018 comes. The last one, of course, if you just check it out, 20 by 1000 times 0.60 would eventually give us about 0.012 mole. And obviously in NaCl we have only one chloride ion per compound or per molecule, so we can say that per chloride ion in the sodium chloride will have 0.012 mole. So, as stated above, three of the solutions contain the same number of moles of chloride ions. In this case, A, B, and D are identical, while C is not identical, which has a different number obviously. So, C will be our correct answer. Moving on, a solution contains 95 ppm of a solute. What mass of the solute is dissolved in 1 kilogram of this solution? Now, we can see that the solution contains 95 ppm of a solute. Okay, so what does 1 ppm mean? We need to understand that. Look, 1 ppm basically means that 1 milligram of solute per 1 kg, which is 1000 gram, whatever you say, per of solution. That's what it is representing, right? So we can see 1 kg of the solution is provided. So this makes it very easy that to find the mass of the solute in grams, what we can do is that we can just divide milligram with 1 kg times the total value of the solution down here, which is 1 kg. Okay, and we all know that so that would be about 95 milligrams. Okay, now we know that 1000 milligrams is equal to 1 gram. So if you want to convert a milligram into gram, so all you have to do is just divide it by 1000 down here. Eventually you will be getting about 0.09595 gram. So our answer here will be C. Moving on, the next one, number 7, a sample of hydrated magnesium sulfate contains 43% by mass, okay, of water. Now, what is the formula of magnesium sulfate? So at first, let's find the molecular mass of magnesium sulfate down here, which would be, if you just do it, MgSO4, that would be 24.31 plus 32.07 plus 16 times 4 eventually we'll be getting our molecular mass of 120.38, I believe, 120.38 gram per mole. So that is the molecular mass of MgSO4. Moving on, again, let's find the water's mass. That is nothing but 2 times 1.008 plus 1600 would provide us 18.016 gram per mole. So we now know the molecular mass of MgSO4 and water, and they already said that 43% by mass of water is provided. So the mass is provided in form of percentage. So if you can formulate equation down here, that 0.43, if you convert it into decimal point just by multiplying with 100, you get 0.43. 0.43 is equal to going to be, the numerator is going to be going to contain the numerator is basically going to contain the molecular mass of water divided by the total molecular mass of magnesium sulfate down here. So the total molecular mass, I think we have found it out a little while ago, which would be uh, 120.38 plus uh, 18.016. Now obviously we do not know what is the value of X, or the number of moles of the water in this hydrated salt, so we need to multiply X with our molecular mass down here. And obviously, since this whole thing basically represents the mass of water, that would be in above at our numerator as well. Eventually, if you solve for X according to my calculations, I will get 5.04, approximately 5, I'm assuming. So the correct formula here would be about B, option B down here. Yes, option B would be our correct answer, because the whole point is to find the value of X, considering uh, the other things remain same in every case when you write the formula of a hydrated salt. Now moving on to the next one, ethanoic acid can be produced by the production of ethanoic by the oxidation of butane. So this is the formula provided, and they told you to find the atom economy. So there's a step-by-step process. First of all, to find the atom economy, the formula would be the molar mass of desired product divided by total MR of all reactants times 100%. So first of all, if I say so, we need to check out the molar masses of each and every. So for molar masses of butane, this would be 4 times 12 plus 10 times 1, giving us about 58 gram per mole. And if you want to find of oxygen, that would be 32 gram per mole. And for ethanoic acid, that would be 2 times 12 along with 4 hydrogen, so 4 times 1 and 16 times 2, eventually giving us 60 gram per mole of molecular mass. Now we also need to check out something else, which is we do have the stoichiometric coefficients provided. So whenever we basically write, we need to take that into consideration as well. So the desired product down here, you can see very clearly, which is ethanoic acid. So we'll multiply the number of moles provided down here with the molecular mass which we just found in order to get the total mass of ethanoic acid. That will be 4 times 60 divided by 4 times divided by 2 times 58, because there is 2 moles, and of course the reactant, another reactant, oxygen, so that would be 5 times 32, right? So eventually if you just multiply it with 100%, what you'll get an answer of 87 point, actually 86.96%. You can eventually write it down as 87%. So our answer would be option D down here. Okay, then moving on, number 9, we can very clearly see the first 4 ionization energies of the elements gallium, indium, germanium and tin are shown. Which values are the first four ionization energies of gallium? Now gallium has an atomic number of 31. Okay, so that would be argon, and then 3d10, then 4s2, 4p1. So that is the ionization energy, the electronic configuration of gallium. Now the first four ionization energies provided. Now we can clearly see that there won't be a big change in when the first three outer electrons are removed, because you can see that clearly the first three electrons, outer electrons, are present in the same quantum shell. The fourth one though is present in another one of a lower energy level, so obviously a higher ionization energy will be required, so must be a big jump between the third and fourth ionization energy. So if there is a big jump between the third and fourth ionization energy, we just need to check out the values down here. So we can clearly see in option D we do not see any big significant change between the third and fourth, so we are not going to consider option D. Again C as well for the same reason. Now this leaves us B and A. Yes, there is a big change, but the change in option B is higher, considering considering the value of the third ionization energy. If you check out the difference in option B is higher, considering the third ionization energy value is greater than the third ionization energy value provided in option A. So option B would be our correct answer. So the whole basis of finding the correct trend is to analyze the whole electronic configuration correctly. Moving on, the next question says sulfur has a higher melting temperature than white phosphorus. Which is a possible reason for this? First of all, sulfur molecules has a greater dipole arrangement. First of all, they said greater dipole than phosphorus molecules. Now, this might not be correct because there is no electronegativity difference between sulfur and phosphorus basically. So there is no the question of a greater permanent dipole does not arises here, because permanent dipole basically depends on the polarity and the electronegativity difference between two molecules, so that will not be a possible reason. Secondly, sulfur has strong covalent bonds. Now melting temperature is not related to covalent bonds, because during melting the covalent bonds do not break, but only the intermolecular forces between the simple molecular structures are broken. So obviously this one and this one are not taken into consideration. Sulfur has a giant covalent structure and phosphorus is a simple molecular structure. Now, okay, first of all, this is wrong because sulfur has actually a simple molecular structure just like phosphorus. So that would not be a possible reason as well, because the whole statement is false. This leaves us with the only option D, where sulfur molecule has more electrons than phosphorus molecules. Indeed, it is correct. The reason why the London forces are more stronger in sulfur molecules than phosphorus. So option D will be the correct answer. Which species are arranged in the order of increasing radius? When we talk about increasing radius, at first we need to consider that whenever electrons are taken in by an atom or a molecule, the whole radius tends to increase because the force of repulsion between the nucleus and the outer electrons increases. So automatically we can say that BCD will be cut, eventually leading us to the only option A down here is the correct answer. Because if you see out here, down here, we can clearly see that K plus, which basically means an electron has been lost. So if an electron is lost, that means the radius is decreasing, so it's going to have the lowest radius among four of them, and also it also has the highest number of protons among four of these elements down here, which is about 19. So that's another uh, point which we can say why K plus has the lowest radius. And then again we have argon, which is 18 obviously, so that would be 18 protons, and since it's not losing or gaining an electron, it's in its elementary form, so we can say it has the second largest radius. And then if I talk about chloride and bromine, obviously bromine is below chlorine, so obviously bromine will have a higher radius than chlorine, so this trend basically is, or is, makes logical as well. So A is the only option. Moving on, which cation will be the most polarizing? So you have the radius provided and you have the charge provided. Now according to Fajan's rule, what do we know? There's a formula that charge density is approximately is equal to charge divided by r squared. So if the radius decreases, the charge density increases, which eventually leads to an increasing polarizing power of cations. So eventually we can say that C and D are cut considering the radius is large. So we can say the radius must be small. And another concerning thing is that the charge must be higher in order to ensure that the charge density is higher, which in turn will increase the polarizing power of cations. So we can say clearly that option A is the correct answer. Okay, now moving on, in the gas phase, PCl5 exists as molecules. They are trigonal bipyramidal. So this whole structure is provided, and you have two axial chlorine atoms. This said, the two chlorine axial atoms are replaced before the three equatorial ones. Which of the resulting molecules does not have a permanent dipole? Okay, so if you just draw the first option down here, they said the axial atoms are basically replaced. So if you just check it out down here, if one of the axial atoms are replaced while the others kind of remain the same. Now for a molecule to not have a permanent dipole, the first things first is that the molecule has to be symmetrical. So if it's asymmetrical, then it's going to have a permanent dipole. So we can clearly see here that the molecule is asymmetrical, considering that all of them goes out while our fluorine down here has a polarity towards phosphorus. So this is going to have, this option A must have a permanent dipole. So that is out of our equation. If we check out B down here, again, they said the axial atoms F and Cl. Again, 2 again 2 versus 3 polarity being diverged out of the main central atom. So this also makes the whole compound polar. So as a result, it's going to also have a permanent dipole because the whole thing becomes an asymmetrical molecule. If you move on to C down here, in B we have Cl, F, F. If you do F, that Cl. Now if you check out in this case, we can clearly see that this time what is happening is that the polarity is being, the three polarities of fluorine are basically are greater than the polarities being given, being diverged away from the central atom of both chlorine, from to the both chlorine atoms down here. So this makes it a symmetrical molecule. This does not makes it a symmetrical molecule either, giving us this as an asymmetrical, making it also asymmetrical as well. And this will also be asymmetrical considering A and D's reasons are kind of same. It says that instead of chlorine there are 4 fluorine atoms, so C and D are cut. I think we missed the answer. The answer was option B, because if you check out option B down here, is that here the molecule is kind of symmetrical, because what is happening down here is that the chlorine atoms, these are the 3 equatorial atoms, are symmetrical, but this is the reason why. And even though the four chlorine, even though the axial atoms are not, the equatorial atoms are basically in symmetrical position. So this is the reason why we can say that PCl3F2 might not have a permanent dipole as compared to A, C, and D, where in both cases the axial and the equatorial positions were in asymmetrical positions. Okay, so B will be our correct answer. Now moving on, which hazard warning symbol would be found on a bottle of hexane? Now, hexane is not toxic and it's also not corrosive as well. So C and D will be out of our options because this represents toxicity while this represents skin corrosiveness. And hexane is this is an example. This symbol represents oxidizing agent, but hexane is not uh, an oxidizing agent, so obviously this won't be in our option as well. So the only option that's left is option A, which makes hexane a flammable liquid, which it is actually. Moving on to the next one, what is the IUPAC name for the hydrocarbon shown? Whenever we try to basically name a compound down here, the first things first that we check out, we try to identify the longest hydrocarbon chain down here. So the longest hydrocarbon chain down here will be this one, because this chain basically contains the highest number of carbon atoms, 1 2 3 4 5 6 7 8 9 10, as opposed to 1 2 3 4 5 6 7 8 9. So if that's the case, and if you now try to do it, then we have 1 2 3 4. So it's 3 4 dimethyl, and then it's 1 2 3 4 5 6 7 8 9 10 10, right? So decane. So the answer would be B down here. The next one, which statement about the cracking of oil is true? The cracking of crude oil separates the mixture into pure compounds. Now that is not necessarily correct, because a lot of smaller compounds basically consists of impurities. So the compounds are not entirely pure. So that would not be taken as a consideration. And the next one, we can see that separates the mixture into fractions. First of all, it cracking does not separate the you know crude cracking does not separate the crude oil into fractions, because that is done via fractional distillation process, so that will be not correct as well. It separates the saturated from unsaturated compounds. So first of all, thing is that cracking also produces smaller chain alkanes and alkenes. So the fact that it separates the saturated compounds from the unsaturated ones is kind of not correct, considering both alkenes and shorter chain alkenes are produced. So the only option would be D, which kind of makes logical, because since it converts a longer chain alkanes and alkenes into shorter chain ones, it is kind of decreasing the average number of carbon atoms per molecule of a hydrocarbon. So D will be our correct answer. Again, bromine and bromine water can be used to test for a carbon to carbon double bond. So when bromine water reacts with 2-methyl-butene, there is one major organic product. Now always remember that one thing's for sure, that is the halogen is going to react with that carbon in the carbon to carbon double bond, which will produce a less stable carbocation as compared to the other carbon. So if you check out option C and D down here, we can clearly see that the double bond was present around right here, but this makes the whole compound as 2-methyl but 1 in. So they basically, in C and D, you can clearly see that the addition of bromine water was done to 2-methyl but 1 in, whereas we are provided the bromine water to react with 2-methyl but 2 in. So automatically we should not consider C and D in our options. So this leaves us A and B. Now if we write 2-methyl but 2 in CH3 down here, So during electrophilic addition, what happens? This bond down here gets broken. So two carbocations will be produced. So you have the one carbocation down here and the another carbocation that might be produced in this one. Here, down here. So the first one, if you check out in this one down here, we can clearly see that the stable carbocation is this one down here, because we know that the stability of carbocation follows this trend where the tertiary carbocation is the most stable, as then followed by the secondary one, and then of course the first one. So since this is the most stable carbocation, so the bromine is going to attack this one, and on the other hand, the other one, which is of course OH minus, this is going to attack the latter carbocation, which is this one, the secondary carbocation. So always remember that the halogen will try to always attack the more stable carbocation, so that and the one in which the carbocation in which the halogen attacks and produces the product, that product will be the major product, because the major product is always stable than the other one, while the minor product is less stable, consisting of the less stable carbocation. So we can clearly say that option A here will be our correct answer down here. Now moving on, number 17. Which of these formulae are correct for compound 1,4-diethyl cyclohexane? Okay, now the first things first, we need to check out the skeletal formula down here. It says 1,4-diethyl cyclohexane. So this is our cyclohexane, and we can see it's connected 1,4. It's the first ethyl group is connected with the first carbon, while the second one is connected with the fourth carbon atom down here. So the skeletal formula kind of matches with the provided compound's name. Secondly, if we talk about the molecular formula, we do have 10 carbons down here, where 6 are here while the rest 4 are here. So if I talk about the number of hydrogen atoms, we have 6 down here, 8, 10 down there, and then if I talk about the rest 8, it is in this cyclohexane hexene base, more specifically speaking. So the molecular formula also matches, and obviously if the molecular formula matches, the empirical formula must match, because you can clearly see that when you simplify this whole thing with the lowest ratio down here, you get C5H9. If you just divide it by 2, so you get the empirical formula C5H9. So I would say three of the provided statements, or the three of the formulas, matches with the compound's name provided down there. Again, if we move on, beta farnesene is an alarm pheromone released by aphids. How many pi bonds and how many sigma bonds are present in this molecule? Now, each double bond consists of a sigma bond and a pi bond. So if there are four double bonds, so easily we can say that there are four pi bonds. So that's already decided. So this basically excludes C and D out of our equation. Now if we can just find the number of sigma single bonds, we can easily get our answer. So if we check out down here, we can see there are 6 sigma bonds, and then that's 7, 8, and 9 for you. And again, if you do it down here, 10, then 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 20, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, and then you have 36 down there. There's 36 down there. So we got about 36 sigma bonds. I think we're missing two more sigma bonds in our calculations. So if we use logic, so we can clearly say that the number of sigma bonds is greater than 31. So our only option would be B down here basically. Again, if we move on, the number 20, which structure is a Z isomer? Okay, if we want to compare between E and Z isomerism, the first things first that we need to consider, we need to take we need to learn basic facts about the E and Z isomerism. Now, in E isomerism, in E isomers, basically, the higher priority groups are present in opposite sides, and in Z isomers the higher priority groups are present in the same side. Now, how do you identify the higher priority groups? Simply, you just find the molecular masses of of each group. Now, we can check in this structure clearly that chlorine is the higher priority group in carbon 1, while the higher priority group in carbon 2 is methyl group. So we can clearly see both of them are in opposite sides. So that makes it an E isomer, not aligning with the answer of our question. If I talk about B down here, we can clearly see that the ethyl group is basically the high priority group in carbon 2, and in carbon 1 obviously it's chlorine. Again, it's in the opposite side, so it's an E isomer. In C and D, again it's the same thing. You have the ethyl group in carbon 1 and the chlorine group, I'm sorry, not actually, the bromine group in carbon 1 and the chlorine group in carbon 2 as the high priority group, but you can clearly see both of them are in the opposite directions, so that kind of makes it an E isomerism, E isomer basically. So the only option here is D, and it kind of makes logical because if you check out in carbon 1 and carbon 2, obviously carbon 2 has the high priority group is ethyl, and the high priority group in carbon 1 is chlorine because it has the highest molecular mass among both of these groups connected to carbon 1. And among this same reason, you can see the ethyl group is the higher molecular mass with both of the groups connected with carbon 2. So obviously it makes it the higher priority group in carbon 2, so that the option D will be our correct answer. Okay, with this our section A is completed. Moving on, let's start our section B. Okay, the first question of section B says that chloroethene and 1-chloropropene are the first two members of a homologous series. Now, 1-chloropropene exists as two geometric isomers. You can see that draw the displayed formulae of chloroethene and one geometric isomer of 1-chloropropene. If you want to draw the displayed formula of chloroethene, it is kind of simple. You can easily just draw it. That's ethene for you, and since there is a chlorine atom attached, we can just connect it with either one of the carbon atom present in the double bond, so that will be Cl down here. And it also consists of one geometric isomer of 1-chloropropene. So obviously at first draw the longer chain or the main chain, which is chloropropene, and they said 1-chloro, so basically it's connected with the first carbon down here in the main propene group. So we can say that this will be our correct answer. Explain why chloroethene and 1-chloropropene are the members of a homologous series. Okay, first of all, what are the features of a homologous series? They happen to consist of the same functional group. They have the same chemical properties. They have the same general formula. So you can easily just write the characteristics as an explanation for the answer of this question. So we can just say that we can clearly see they're consisting of the same functional group down here. So we can say they both have the same functional groups and also have the same general formula with similar chemical properties. Why am I saying similar chemical properties? Because I've already stated here that both of them consists of the same functional group, which is the carbon to carbon double bond, the alkene functional group. And the functional group basically determines the chemical properties of a compound. So we can easily say both of them also consists of similar chemical properties as well. Moving on, explain why one chloropropene exists as two geometric isomers, what one chloroethane does not. Now if we just analyze both of the compounds down here, analyze the compound, we can clearly see here that both of them consists of the alkene functional group, so there is restricted rotation in both of the compounds, meaning that the groups which are connected to the carbon, they are kind of distinct to each compound. They're not going to interchange each other. So that's one reason. The second reason that why one chloropropene has geometric isomers while this one does not, it's because you can clearly see that in each carbon atom in the carbon to carbon double bond, there are, you know, uh, there are two different groups attached in one chloropropene. But if you check out in chloroethene, one of the carbon atom involved in the carbon to carbon double bond consists of two same groups attached to it, which is the hydrogen atoms. So in one way we can say that uh, the atoms which are connected to the carbon to carbon double bond in one chloropropene can exist in both sides in different forms. The reason why it provides it has the ability to have geometric isomers as compared to its counterpart down here, which is chloroethane. So we can write the first reason is that this is because there is restricted rotation around the carbon to carbon double bond in both molecules. One chloropropene has two different groups attached on of its carbon in the double bond, while as opposed to two hydrogen atoms attached, as opposed to two hydrogen atoms attached in one carbon of carbon to carbon bond double bond present in chloroethene. So this is one these are the two reasons why one chloropropane exists as two geometric isomers but one chloroethene does not. Again, chloroethene and 1-chloropropene are both monomers. So they told you to draw the structure of poly 1-chloropropene. So in this case, if we just draw, they said that both of them are monomers and 1-chloropropene. So if we basically draw 1-chloropropene down here, we have chlorine, chloropropene, that's H, and that's H. Now obviously when you draw the monomer, the double bond basically, when you draw the structure of the polymer from the monomer, so the double bond basically breaks, so eventually you get something like this. And providing n, because we do not know how many monomers create this polymer down here, so this will be your correct answer. Moving on, the polymer of chloroethene, known as PVC, is used to make water pipes and gutters, which was previously made of metal. So there's two advantages of using PVC instead of metal in water pipes and gutters other than cost. Okay, so first of all, what we can say that the previously given information that the material which was used previously to produce water pipes and gutters was made of metal, and now PVC is used. Normally, PVC tends to have lower weight, which leads them to provide a lower density as compared to metal. So that's one advantage we can say, that other than cost, that PVC is less dense or has less weight as compared to a metal. The second thing is that metals tend to corrode, especially iron, as they react with oxygen to produce hydrated iron 3 oxide. So in the case of PVC, there is no concern of rusting, so we can easily say that PVC does not corrode or rust, unlike metal. Our next question, we can clearly see number 22, that the diagram shows the arrangement of electrons in the energy levels of a sodium atom. So here you have some energy levels provided with obviously n is equal to infinity, the last one, and this is the first quantum shell, n is equal to 1. Now they said here, give the reason why the two electrons in the n is equal to 1 energy level are represented by arrows pointing in opposite direction. Now arrows pointing in opposite direction clearly indicates that the electrons have opposite spin, so we can just write to show that the electrons have opposite spin. Explain whether or not all of the electrons in the n is equal to 2 energy level have the same energy. uh, okay, if you check in n is equal to 2 down here, you have to understand that not all of the, even though all of the electrons are present in the second quantum shell, within the second quantum shell you have s and p orbitals, right, in the sodium atom. So if I know this, that we have 1s2, 2s2, 2p6 basically. No, actually it is about 2p6, and you have 3s1. Yes, that kind of makes sense. So you have 11 protons, and you can electrons, not protons. We can clearly see that in our second quantum shell, the 8 electrons, as you can see, are divided between s and p orbitals. I mean orbitals or subshell, whatever you call it, and obviously they don't have the same energy, uh, because obviously the electrons present in the p orbital tends to have a higher energy than the ones electrons present in the s orbital or subshell. So we can easily say the electrons present in n is equal to energy level do not have the same energy. So we can write it down that in n is equal to energy level, some of the electrons exist in a s subshell or orbital, and while some exist in the p subshell or orbital. They don't have the same energy because electrons in p orbital have higher energy than the ones present in s. Hence, not all of the electrons have same energy. So this will be your complete answer for this question. Moving on, name the shape of the orbital occupied by the electron in n is equal to 3 energy. Now we can clearly see 3s1. S basically represents a spherical, s orbital is basically has a spherical shape, so we can say the shape is spherical. Moving on to the next one. Samples of germanium consists of 5 isotopes, 4 of which are stable. You can see that the fifth isotope down here, they said germanium 76 is radioactive but with a very long half-life. Calculate the mass of the fifth isotope of germanium. In order to calculate this, at first let's calculate the abundance of the fifth isotope, since all other ones are provided. So abundance of fifth isotope will be 100 minus 20.5 minus 7.8 minus 36.5 minus 7.8. That would provide us 27.4% as the abundance of the fifth isotope. Now if you find the relative atomic mass, basically if you find the relative atomic mass, we need basically a formula for this. So if you can find the relative atomic mass, which they have been provided, the whole germanium, which is 72.6. So if you produce a formula of relative atomic mass is equal to, we all know that it's the total summation of the molecular mass present multiply the total solution of the total summation of the molecular mass, which you basically find by multiplying the abundance with the mass number divided by 100. So that would be 100. 70 times 20.5 plus 73 times 7.8 plus 74 times 36.5 with 76 times 7.8, and then eventually you have 27.4, which would be, we don't know the mass number, so we just need to find the mass number, so that would be x times 27.4. Now if you solve for x here, eventually you will be getting x is equal to be about something like, if you do it down here, x is going to be equal to about, I saw in my calculation, about 1961.8 divided by 27.4, which will eventually give us 8 27.4 would be about 71.598. So you can just give it as 72 as well. So that's the mass number. We can check it out. We can see that. So that would be our mass number of the fifth isotope of germanium. Moving on, give the main reason why the answer in A1 should not be coded to more than two significant figures. Uh, because it's pretty simple. Mass numbers are not provided in significant are not provided in decimal points. They're most likely given as an integer or a whole number. So that's why it's important that we basically provide the answer of mass number as two significant figures. We can, because during our calculation we could see that we got a value with a decimal point of obviously having a value of more than three or four significant figures. So if we could code the answer to two significant figures, it becomes a whole number. So that's why. So we can write it down. The mass number, or in other words, the nucleon number, must be an integer. Okay. Moving on, the radioactive decay of germanium 76 forms stable atoms of selenium 76. You compare and contrast the atomic structure of an atom of germanium 76 with an atom of selenium 76, basically. Okay, the first difference, if we see, is that germanium has 32 protons and selenium has 34 protons according to the periodic table. So we can clearly see the first difference. Whenever they say compare and contrast, we need to get some differences and some similarities. So let's at first write the differences. So germanium has 32 protons as opposed to 34 in selenium. So that's one difference. Second difference, we can say that germanium has, now we know the number of protons, right? And we can clearly see the mass number provided. So we can just write 76 minus 32. That would be 44 neutrons, as opposed to, if you subtract 34 from 76, 42 in selenium. Again, if we can also write another thing, the number of electrons, uh, this line you can just easily just copy and just you can easily just copy you can write electrons as opposed to 34 in selenium. So these are the three differences. If I talk about the similarity, both of the atoms have the same mass number, so that's like a common sense, and the answer is provided in the question. Both have the same mass number. Okay, moving on to the next one. A sample of volatile liquid X was vaporized at 473 Kelvin, and you got the pressure is this much with 3.50 gram of X occupying 1.79 dm cube. Calculate the number of moles of X in this formula. That is, we can use the ideal gas equation, as they said PV is equal to nRT. So if we just make N the subject, we have PV divided by RT. So that would be what? That would be, if we just convert the volume into, if we just convert the volume into cm into meter cube, so that would be 0.00179 meter cube, considering if you just divide it by 1000, so you'll be getting that. You just have to divide dm cube into 1000, we get meter cube in that form. So if you just plug it in, 179 times the pressure, which is obviously this one, we can just write it down like this, which is the Pascal is the SI unit, so we don't have to convert the pressure again. Since dm cube is not the SI unit, we need to convert it into meter cube. That's why we did it. The next thing, just multiply 8.31, the rest of the values, provided the temperature is about 473 Kelvin. So you can see eventually you get the value as 0.0501 moles. That is the amount of moles present in your X sample. Moving on, deduce the relative molecular mass of X down here. Now you can clearly see that the mass is provided, and you also know the moles. The relative molecular mass is pretty simple, which is Mr is equal to, you have 3.50 divided by 0.0501, that would be 70 gram per mole. That would be the relative molecular mass of X. Again, if you want to find the empirical formula of X, so let us at first find the moles of carbon, which is, since the mass is provided in percentage, you can just easily divide it by its molecular mass, and this one as well, 43.1 divided by 1, so 1. So eventually what you get is the ratio as about, you get about 7.1417 as opposed to 14.3. So now if you just find the simple ratio down here, so what you get is, you get about 1:2 if you divide both of these by 7.1417. So the simple ratio is 1:2, so we can say CH2 is our empirical formula of X. Again, they say to deduce the molecular formula of X, and now this is very simple, since we know the we know both of them. We know the molecular mass, which is 70 down here, and you also know the the empirical formula down here. So you can just write X times the empirical formula CH2, which is equal to the molecular mass of the molecular formula 70. So X here is going to be 70 divided by 14, which is 12 times 2 times 14 is basically the molecular mass of the empirical formula down here. So what you get is 5. So eventually we can say the molecular formula would be C5H10. Moving on, a few drops of a purple solution of acidified manganate 7 were added to a sample of liquid X and shaken. The solution remained purple. State what can be deduced about the structure of X from this experiment. Now, acidified potassium manganate 6 is basically used as a reagent in test of unsaturation. Since the color was not, the color did not disappear, or in other words, the potassium manganate did not get decolorized, we can easily say that no carbon to carbon double bonds are present in the structure of X, or you can say it's not an unsaturated compound, in other words as well. Identify by name or formula two possible structural isomers of X using your answers to A4 and B, basically. Now, in order to solve this, if you want to basically find one possible structural isomer, if you see A4 and B. So we know that there are in B, we basically stated there are no carbon to carbon double bonds, so which makes it not an alkene. And in A4 we know the molecular formula is C5H10, right? So we can easily it's an alkane basically, considering from B, so we can just easily give any two structural isomer. So we can write this down here, C5. So one would be, obviously we can say one would be obviously a cycloalkane. We can just give one as a cycloalkane, so that would be uh, something like this. So there are 10 hydrogen and 5 carbon, so that's one thing. You have a cyclopentane as a structural isomer as per stated, as per deduced from the molecular formula provided. Another thing that might happen is a cyclobutanes, where you have 4 carbons, one of the carbon being attached to any one of the, it could be with this one, this one, or this one, doesn't matter. So you can just connect it with any of the carbon present. So this will be our cyclobutane. So these are the two possible structural isomers of X according to B, which we have deduced from the provided answers of B and 4. Moving on, chlorine reacts with both alkanes and alkenes. 3 steps in the mechanism for the reaction of chlorine with butane to form 1-chlorobutane are formed. Okay, name the mechanism and type of this reaction. Now this is pretty simple. We know that uh, when chlorine reacts with alkenes and alkenes, it results to the production of halogenalkanes. So whenever halogenalkane is produced, the mechanism is basically free radical substitution, uh, free radical substitution mechanism, and obviously the type of the reaction would be substitution reaction, considering one of the hydrogen is basically substituted as for a halogen. So yeah, this is the answer. Give the essential condition for step 1 to occur. Now for step 1 to occur, which is basically fission, you require the presence of UV radiation, otherwise you won't be getting the necessary energy. So we can say ultraviolet radiation is an essential condition for step 1 to occur. Name the type of step illustrated in step 3. In step 3, you can clearly see that the radicals are reacting with the unfissioned chlorine in order to produce the final halogen. So this is known as propagation. This step 3 in the mechanism. A different type of step other than the ones shown also occurs in the reaction. Describe this type of step, including 2 possible examples which might occur. Now, after propagation, where the main product is produced, the radicals react themselves, the ones which are left as reactants. This process, and the process in which this happens, it is known as the termination step. So it is the termination step where 2 free radicals, these are known as free radicals, as we can see, each consisting of an unpaired electron. So these species consisting of unpaired electrons are known as radicals, which have been produced from step 1. So in the termination step, 2 free radicals join together to form a molecule to form a and no, but you have to understand one thing: no other product is created. I mean, the product here is obviously halogen alkane, but halogen alkane won't be produced in this case, and no other product is produced. So if I give you um, one example we can say easily is the two free radicals, right? So let's say CH3 CH2 3 dot plus Cl dot, giving you the halogen alkane down here. And if there is any other two free radicals present, we can say that uh, this one, two free chlorine radicals reacting to produce chlorine. So this is the two possible equations or reactions that might happen in the termination step. There are others as well, but these are the two possible examples that I've given in this answer. Moving on, chlorine is not a polar molecule, but it can react with alkenes through an electrophilic addition reaction. State what is meant by the term polar molecule and why chlorine is not polar. Now, first of all, you need to understand that in a chlorine bond, both of them have the same electronegativity, so there is no electronegativity difference here. And so we can say this is not for polarity to exist. Polarity basically means what? Again, they say to define a polar molecule where one of the atom in a bond consists of partially positive charge while the other contains a partial negative charge. And for this to happen, you will be requiring an electronegativity, a large significant electronegativity difference to be present. But in this case, both of them are of the same element, so there are no electronegativity difference down here. So we can easily say that chlorine is not a polar molecule. So we can say a polar molecule is a type where one end of an atom consists of partially positive charge while the other end has a partially negative charge. Chlorine is not polar because it has no electronegativity difference. This is the main reason. Explain why chlorine reacts with alkenes even though it is not a polar molecule. Now that's a nice question. First of all, we know that in alkenes we have the carbon to carbon double bond, so we have pi bond along with the sigma bond present. So the electrons in the double bond of the alkene, what happens is that they distort the electron cloud in the chlorine molecule. So this is the reason why chlorine are able to react, because we know that like charges ripple. So the pi bond electrons basically have the capability to distort the electron cloud or the electrons present in the chlorine molecule, which helps to induce a dipole. So we can say the electrons present in the pi bond of the carbon to carbon double bond in the alkene has the ability to distort the electron cloud in the chlorine molecule. has the ability to distort the electron cloud in the chlorine molecule, hence inducing a dipole, which causes it to react. So the formation of a dipole due to this phenomenon allows chlorine to react with alkenes even though it's not a polar molecule. Okay, moving on, sulfur hexafluoride SF6 is used in the electric power industry as an insulating gas. It can be used in this way as it is very unreactive. Now, fluorine reacts with sulfur to form SF6. Impurities of S2F10 and SF4 also form and must be removed because they are too reactive. So give the name of S2F10. Okay, so there are two sulfurs, so we can easily say disulfur. And there are 10, so we know that when our 10 carbons are present, it's a decane, so we can say it's a deca fluoride since there are 10 fluorine atoms present, so that would be deca fluoride. Okay, the molecules of S2F10 consists of two SF5 units linked by a SS bond. So this is the dot and cross diagram. They told you to complete the dot and cross diagram. So eventually they provided the outer electrons of F. So each F fluorine atom is going to share about one electron, while the sulfur will also, share one electron, considering it has six electrons, or there's six electrons in its outer shell. So we can say that. So in this case, between the sulfur, one sulfur is going to donate one of its electron, while the other one donates another one. So this makes it 8, and then you have one electron coming from each fluorine down there. Uh, Repeat the same process down here as well. Down here. So this will be our correct dot and cross diagram. As you can see that the electron clouds are fully complete for each, for fluorine as well as sulfur. And this is it. Remember that they told you to use dots for the sulfur electrons and crosses for the fluorine electrons, so that's why I used crosses for the fluorine atoms and dots for the sulfur. This basically carries 1 mark. Now complete the table, the last one question basically, that complete the table clearly showing the shapes of the other two molecules and the FSF bond angles. Okay, first of all they gave S2F10, so this basically means that, so basically 2s is connected, and then we already have an idea of how the SF6 molecule would be, so it's going to be a pyramidal shape, something like this or something, yeah. And then that one. Okay, and this F will go away where the S is connected, so we can just cut the F down here and then disconnect another S, and then this repeat the same thing, and that's it. This is our structure. So we have 2 sulfur and 10 fluorine, as we can see. Okay, and obviously we can clearly see the FSF bond angle has a 90 degrees between them, so that would be 90 degrees. Then they told you SF4. Again, if we cut these two, or we can also cut these two, whatever is it, we have to just basically cut two fluorine atoms from the horizontal plane, not the vertical, from the horizontal plane. If we cut two fluorine atoms, so eventually we'll be getting 4 with fluorine atoms left. So if you just cut 2 down here, so that would be F F F F. So that is our answer. Now regardless of whatever you see, there are many angles here. It could be 180 degrees, or you can just also say it is about this FSF down here. It is about, you can say, mm, not this one. This one could be 90 degrees as well. This part could be 90 degrees, so we can just give any one of the angle. 180 degree would suffice. Moving on, justify the shape around the sulfur atom in both SF6 and SF4. Okay, in SF6 you can clearly see that there are 6 bonding pairs of electron, 1 2 3 4 5 6, and there are no lone pairs. But if you check in SF4, there are 4 bonding pairs of electrons, but there is one lone pair, considering uh, the one of the bond has been not being produced. So the electrons, due to the lone pair being present, the electrons will basically repel to be far away as possible, so that the maximum distance is maintained between them. This is the justification for the shape for SF4 and SF6. Okay, so we can write sulfur has 6 bonding pairs in SF6 and 1 lone pair, as opposed to 4 sorry no lone pairs, 1 lone pair in SF4. Due to the presence of lone pairs, repulsion between the electrons is higher, which leads to greater maximum separation. So due to the greater maximum separation, the shape of SF6 and SF4 is kind of different. Okay, moving on, SF4 and S2F10 are reactive, but SF6 is unreactive. Suggest reasons for this, considering the shape and bonding in each molecule. Okay, now in order to solve this, we need to analyze the compounds present down here. First of all, if you say for SF6, here there are 6 strong fluorine atoms connected covalently with the central sulfur atom. So these bonds are quite strong enough, producing a giant covalent structure. So we can easily say, and all of them you can clearly see that they are kind of, the molecule is kind of symmetrical, so this makes the whole compound non-polar. So we can easily say that the energy required for breaking these bonds down is pretty much high, and that is the reason why SF6 is kind of unreactive uh, compared to its counterparts present, which is SF4 and S2F10. Meanwhile, if you check out the other ones, for example SF4 down there, what do you know about SF4? That we do have a lone pair of electron present uh, in one of it, in the sulfur atom, considering that an empty orbital, considering there is an empty orbital, since there are no two bonds present. Uh, so this kind of makes, due to the presence of the lone pair of electrons, the sulfur becomes more reactive, as opposed to the one present in SF6. Okay, so that's one reason why we can say that SF4 is more reactive than SF6. And why S2F10 is reactive? Well, it is because of one thing you have to understand, that is in S2, in the SS bond, basically in S2F10, which we drew, the SS bond is kind of weak as compared to the SF bond present in the SF6 one. So since the SS bond is kind of weak as compared to the SF bonds, which are only present, there is no SS bond in SF6, right? So since the SS bond is present in S2F10, and since it's much more weaker than the SF bond present in SF6, it's kind of much more easier to break it down. So since less energy is required, so as a result we can say S2F10 is more reactive than SF6. So since we have jumbled out all the logics in our brain, so we can just now just easily summarize and say that SF4 has a lone pair of electrons as opposed to none in SF6, making the sulfur atom more reactive than okay. There are 6 fluorine atoms covalently bonded with sulfur in SF6, making it a non-polar molecule, non-polar symmetrical molecule, for which high amounts of energy is required, because we know that non-polar bonds are much more harder to break due to the high energy required to break the bonds, making SF6 in overall unreactive. The SS bond is weaker as opposed to SF bonds, and so its presence in S2F10 makes it reactive than SF6, where it is absent. So this is the complete answer for this question down here, and with this our section B is complete for this paper. So that's it for today. Basically we'll meet in the next video with another exciting paper with some great doubt solutions. So goodbye for now. Thank you. Stay tuned and subscribe to our channel Exam Essentials at YouTube. Bye bye.